So first, with trig, a lot of times in high school you use degrees. In calculus, they don't use degrees, they use radians. Okay, so what I want to do today is to show you that radians is actually easier to work with when you don't have a calculator. If you go all the way around a circle back to the start, how many degrees is that? 360. So you're working with 360 and fractions of 360. So like 360 divided by 6 is what? I'm giving you an easy one to do in your head. 60. But that's the only easy one, and some of you are saying that wasn't easy. But you not using a calculator and having to divide 360 into pieces and then multiply it by like 7 is not really easy. But radians, the numbers are 2, 3, 4, and 6, not 360. So they are easier to work with without a calculator. And in calculus, we don't use degrees ever. So first, let's just talk about switching between degrees and radians. They're just both a measure of an angle, just a different type of measurement. So we have to start with something, and let's say that 180 equals pi radians. What's pi equal to? And that's wrong. Why is that wrong? Right, that's not exactly equal to 3.14, so we need what? Little squiggly equals. Okay? So it's approximately equal to 3.14. It's an irrational number, which means the decimals don't have a pattern. They repeat, or they don't repeat or have a pattern. They go on forever. That's an irrational number. So 180 is equal to pi. You can use this one fact to convert any degrees to radians or radians to degrees. So for example, if I wanted to know what 225 degrees is in radians, not easy without a calculator, but let's do it. So what you do is you take your fact that you know, 180 degrees equals pi. So you write that down. Now what I want to happen is something to this statement. I want to do something to both sides, because you can always add numbers to both sides of an equal sign. You can multiply, you can divide, as long as you do the same thing to both sides. So I want to do something to both sides of this, so that in the end, 180 says 225 instead, and then whatever's over here is the answer. Does that make sense? So I want to do something so that I end up with 225 on that side. Whatever's over here is how many radians that is. Not an easy task without a calculator, but let's do it. So the first step is I could divide both sides by 180. What would that leave me on this side? 180 over 180? 1. Okay, so far so good? I just divided both sides by 180. Now what do I want on this left-hand side? So let's multiply both sides by 225. So I'm going to multiply both sides by 225. So 225 degrees is equal to 225 times pi over 180. So that's like it. Now if I reduce that to its lowest terms, that's what it would be equal to in radians. So what divides into both of these? What could we reduce that by for sure? 5. 5 would be good. So maybe we know what 5 into 225 is, and maybe we don't. Let's say we don't. How would we do that? Any ideas? A couple. You could do long division. I would probably do this myself. How many 25s are in 225s? Think of it as money. Anything that ends in 25, you can think of it as quarters. If you had $2.25, how many quarters is that? 9 times 25. Okay. Anything that ends in 25, 75, or 50, you can do that. Think of it as quarters, saying how many quarters are in there. Usually people have no problem. Now I'm trying to find a 5. This divides into 5 by 5. So 225 is 9 times 5 times 5. What about 180? Well, 180, you could do long division again, but I would probably do 18 times 10, and 10 is what? 5 times 2. So 180 is 18 times 5 times 2. That allows me to cancel out a 5. Will anything else cancel? Look at what we have left. The 9 and the 18, won't they? How many will we have left? A 2, right? Because this is 9 and 2. So we'll have a 2 left. On top we have 5 pi. On the bottom we have 4. So 225 degrees is equal to 5 pi over 4. You can practice doing a few in the book. Okay? And we'll do one going the other way. But this is not really an important... It's important to be able to do it, but you're always going to see radians. Where do you see degrees? If any of you have taken linear algebra, they usually use degrees in linear algebra. In calculus, they use radians. So you do sort of need both. I always convert to radians because to me, it's really easier to think about. And I'll show you why in a minute. But let's do another question where I start with something in radians and convert it to degrees. Okay? So let's write down say 3 pi over 4 radians is equal to blank degrees. So we do the same thing. Write down the one fact that you know, or that I told you know, which is 180 degrees equals pi radians. Okay? So what do we want to do to the 3 pi over 4? We want to end up with, we start with what we know, 180 degrees equals pi, and we want to do something to this so that there is a 5 pi over 4 over here, and whatever's here will be the answer. This is always way, way easier this way.
Where did we get the 5 pi over 4?
Oh, 3 pi over 4, thank you. Does that look like a 3? Yeah. So we want to do something to the pi to get 3 pi over 4. What would we do? Times it by 3. Divide it by 4. Do that to this side, and you've got your answer. Now we have to work this out, but you don't really have to do more than just that. So we wanted a 3 and a 4 with the pi here, so we multiply both sides by 3 over 4. So now I need to figure out what 3 times 180 divided by 4 is. So what can we cancel? The 4 can go into 180. Does it go in just 2 or 4? 180, something we know with 180. 2 times 90, 18 times 10. This is 2 times 9, this is 2 times 5. So my question is, does 4 go into this? What's 2 times 2? 4. So 180 is 4 times 9 times 5. So, and there's nothing else to cancel. So 9 times 5, 45 times 3, 135. Okay, so that's converting, and it might seem strange, but if you try a few, it's really easy. What you do is you start with 180 equals pi, and do something on both sides so that you have what you want, okay? And it's the same for both. So there's a few examples in the book you can try for that. Okay, so what we're going to do now is I'm going to attempt to convince you that radians is better than degrees, okay, in my own personal opinion. So, I may not convince you, and that's fine. This is, if I said 225 degrees, and I wanted you to draw that on here, how do you do it? Any ideas?
Where's your starting point for 0?
Always here. And we always go in this direction. Okay, so 90, 180, because this is 90 degrees here, another 90, this would be 270, and 360 back to the start, okay? So where would 225 lay? In between here somewhere. I might have to guess, or we could figure it out exactly, okay? So that's degrees. Now, what was that equal to in radians? That was the one we did, I believe. 5 pi over 4. I'm going to draw it exactly. So 5 pi over 4 without trying to add or subtract from 360 or from 180 or doing anything fancy. Okay, here's 0. Now I want you to think of pi not as in a pie like an apple pie, okay? I want you to think of pi like a half moon Joe Louis. You know what I mean? So let's draw it. One doesn't look very nice, but there it is. Kind of rounded. What is it? It's like cake with frosting in the middle. You can get weird ones. You can get white ones with jam in the middle. Those aren't very good, but okay, that's a pie. Do you know what I mean? So if you get to eat a whole pie, starting here, we're going to lay our pie out. Here's the start always. Here's our pie. If we eat a whole pie, that means we get to eat from here all the way around to here. And remember, pi was equal to 180? Right. What if I got to eat only to here? How much of the pie do I eat? Half of the pie. That's pi cut in half. Half of a pie. Do you understand? So we actually, to go all the way back to the start, there's 2 pies in here. Okay, this is 2 pies. So let's say we get to eat 1 piece, 2 pieces, 3 pieces of these, and the cut marks are right here. Then how far are we? 3 pieces out of pies that are cut in 2, right? 3, that's 1.5 pi. Does that make sense? 3 pieces, and the pies were cut in 2. And back here is the start. 4 pieces, and the pie is cut in 2 is equal to 2 pies. Okay. Now, what if we wanted to draw this? What do you think this means? We get to eat how many pieces? 5 pieces of the pie, but they're cut into how many? Quarters. So they're cut in 4 pieces. And we get to eat 5 of them. So let's look at what that looks like. So if each pie is cut in quarters, so here's a pie, where would those cut marks be? So there's a whole pie. We'd have to cut it in half and then in half again. Is that quarters? Yep. We want to eat 5, so you get to eat that whole pie plus how much? A quarter of the next one. So here's our pie. 1, 2, 3, 4, 5 pieces. We land right here. 5 pi over 4. And it lands right in the middle because they're quarters. So there's 5 pi over 4. Okay, let me give you another one. let's say, 11 pi over 6. We want to draw it. Okay, so that's all we're doing. We're taking an angle and we're drawing it. 11 pi over 6. I have no idea what that is in degrees, but this is saying that our pi is cut into how many pieces? 6. So how would you do that? Like that? So that's 6 pieces. And then, do we need more than 6? Yeah. Okay, so let's count out 11. We always start here. That's the start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's the angle. Now, what's 1/6 in degrees? How many degrees is a 6?
30.
30. Yeah. So this is, what would this be? If that was 360 all the way around and that size is,
330.
so that would be
330.
330. Yeah, so that's another way to convert. If you draw it, you can usually figure out how big it is. Because pi over 6 is 30 degrees. Pi over 3 is 60 degrees. That's a bigger piece, right? So that's the bigger one. What's pi over 4? Half of a half, so 45 degrees. Right, so if you know what these three are, if you draw the radians, you can usually figure it out if you wanted to convert that way too. So that's another option, how to convert. Right, so what I said was pi over 6 is 30 degrees, and we have one piece left in here. Right, so that would be 360 minus that one piece, so it would be 330 degrees. That's what. So it's just a different way to figure out what it is to convert back and forth. If you're given the radians, you can always draw it. You could do the same with the drawing the degrees and then figuring it out from there. Okay. So what I have on this sheet. Does everyone have a sheet? So the first thing I had is 180 equals pi radians. So there it is. We did that. So this is really small, but let's make it bigger. This says CAST. And you might have called that the CAST rule. Right? In the calculus book, they call it all students take calculus. Yeah, grown. That's what they put. That one's a little better than CAST rule. Why? Any ideas? This is the first quadrant, right? If here's your start, then this is the first quadrant. That's the first one you go to, then the second quadrant, third quadrant, and that's the fourth. So it kind of makes more sense to start with A than it does to start with C, but either way, okay? So you need to know the CAST rule. So what I showed you so far is how to draw an angle. So if we see an angle, we cut the pi up into pieces and we count how many pieces. Okay, and we're going to do a whole bunch more of those. The second thing you need to know is the CAST rule and what it stands for. Okay, so, and maybe you didn't even see the CAST rule. How many people use the unit circle in high school? So half. I don't use the unit circle. You can certainly go back and do that. It's easy to recreate if you sort of remind yourself how it works. If you use the unit circle, you don't need the CAST rule, but it's still helpful to know the CAST rule for a few other things. So, what do these letters stand for? So, all A stands for all. And what it means is that all trig ratios are positive here. And I'll tell you what those trig ratios are in a minute. Sine means that sine is positive here, which implies that cos and tan are negative. Okay, so cos and tan are negative. So that's sort of what you want to remember. If it's in the S, then sine is positive, but if you're trying to find cos and you landed your cut mark in there, then cos is negative. Okay, so we'll practice this in a second, but I just want to write them all down. What's T?
Okay.
Oh, sorry. Tan is positive, which means what? The other two are negative. And the last one, C, is cos is positive. So sine and tan are negative. Okay, so we'll go back to that in a minute. What are these three drawings? It's just showing you how they're split up. This is pi over 3 would be 1, 2, 3 pieces of pi. Pi over 4, 1, 2, 3, 4. I find it helpful to put the little circle there so that you can picture it as a pi and that those lines are cut marks, but you don't always see them. Sometimes you just see the line, and this would be 1, 2, 3, 4, 5, 6, 7. Okay? Now, we've got a table here, but I'll talk about that in a minute. Okay, so we'll go back to that. All right, so let's just talk about the trig ratios for a second. Okay, so sine, we usually put a theta, but it could be an x or anything. But it has to have something after it. Sine by itself, just S-I-N, is a symbol. It doesn't actually mean anything unless it has an argument. That's something after it. Going back to square roots, because I always go back to square roots. If I wrote down this, it looks funny. Hopefully that looks funny to you because I didn't put an argument. I didn't even put an X under it. I just put the symbol. You can't just put symbols without the argument. That would be like putting cube, that's an exponent, with no base. That's a symbol, but without saying what it's for. You don't put that and then say is equal to 8. That's an exponent is equal to 8. The argument's missing. That looks weird. You wouldn't do it. You wouldn't put a square root without putting what comes under it. You cannot put a trig without an argument, or to a mathematician that looks weird. To you it doesn't because you're just messing up. But it should look weird because it always has to be the sign of something. It's like a square root with nothing after it doesn't mean anything, okay? Or else you're just you're writing the square root of a number is, right? If I did that, that would be okay as sort of like an abbreviation for a sentence instead of writing the word square root. So putting a sign, which I did on the last page without an argument, was because I was using it in a sentence. Sine is positive here, tan is positive here, and cos is positive here. Those were abbreviations for the actual words. You know what the actual words are? Sine is spelled with an E at the end. Tan is what? Tangent. And cos is cosine. So those were abbreviations I used, so I could use it that way because I wasn't saying take the sign of something. So we don't just use it without an argument. Okay, so that's the first thing. So if you say sine equals 1/2, you're wrong.
It doesn't make sense. It's like saying square root equals 4 with nothing under it. That doesn't make sense. It doesn't mean anything. Okay? So sine theta, sine x, sine, and we might put an angle there. Okay, so sine theta. On a triangle, here's an angle. This is indicating what? That little square means that it's 90 degrees. The side opposite, or across from it, of the angle is called the opposite side. The hypotenuse is across from the right angle. And what's this side called? Adjacent. It's the side attached to the angle, okay, or beside, adjacent. So, do you remember these? Sine is, you remember? Opposite over, right, SOHCAHTOA, opposite over hypotenuse. Cos is adjacent over hypotenuse, and tan is opposite over adjacent. Yeah, so there might have been an acronym that you had for that. SOHCAHTOA is the most common one. I don't know it by that one, so I had to look up here to write it down. I could probably try to memorize that, but I've never used my brain space to memorize that like that. Because in grade 10, when I first learned it, that's not the rhyme they told us. They told us, you want the bad one or the good one? So salty old Harry caught a herring traveling over the Atlantic. That's the first one. And then we changed it to sleazy old Harry caught AIDS and herpes traveling over the Atlantic. So, yeah. So, but whatever way you memorize it is fine. Okay, you can make up a totally new rhyme, but yeah. So why are they called ratios? A ratio is a fraction. So the trig are fractions, and these are how they're related. They come from a triangle. That's where they come from. Now, what about the other three trig ratios? So cosecant, secant, and cotangent, or cotangent. What are they the opposite of? They're actually just the, not inverse, that's the wrong word. If you're in French, you would have said inverse. That's the right word in French, but not in English. What's it called when you flip over a fraction? Reciprocal, right. Inverse is something else, because there is trig inverse functions. They have a little -1, but they are not these. So inverse is actually something else, which you do in calculus, but not in pre-calculus. So sine is, this is how you show a reciprocal. It means flip over the fraction. So cosecant is the reciprocal of sine. So that would be, if you were looking at a triangle, hypotenuse over opposite. Secant is the reciprocal of cos. So it would be hypotenuse over adjacent. And cotan is the reciprocal of tan. All right. So you remember 3 and you know the other 3, but these are sort of, to me, they seem backwards. These two match up. See the one that starts with an S? The reciprocal starts with a C. And the cos, the reciprocal is the one that starts with an S. If they matched, it would be easier to remember, but you have to remember that they're opposite letter. So this one starts with an S, and the reciprocal is cosecant. And cos starts with a C, and And they just named them that, they shouldn't have maybe, but we can't change that. Cotan's easy to remember, that's the reciprocal of tan. Now there's one more identity that's really useful, that I use all the time, which is tan is equal to sine over cos. Now when we were doing fractions, if I had a fraction 5 over 2 and then another one which is say 4 over 2, let's not reduce that. The 2's actually cancel because they're the same on top and on bottom. There's a half on top and a half on bottom. They'll actually cancel. You can just ignore them. And the answer is what? 5 over 4. All right? So that's something we did see before. You could take the reciprocal, the 2's will cancel. But if there's a divided by 2 on top, a divided by 2 on bottom, they cancel. They're the same thing on top and bottom. Look up here. Let's go back up. Here's sine, and here's cos. And I'm telling you that tan is those two divided. Sine over cos. Look at the fraction. What's the same about them? They're both over the hypotenuse. That cancels. So it's equal to opposite over adjacent. You see it? Yeah. I use that all the time, because if you know sine and cos, then you just divide them. And it's actually just the top. Yeah? Oh, yeah, thank you. Yeah, yeah. I flipped over the wrong one. Right? Yeah. I should have flipped over tan, and I didn't flip over tan. Okay. So this is also very useful. Okay, it's useful for more than just finding the trig values. It's actually useful in calculus because you're going to have to simplify things. And to do that, one good technique is always convert everything to sine and cos, and then stuff will cancel. So knowing that tan is sine over cos really is useful in all areas of math in any course you ever take. Having that is good. Okay. So that being said, this is all kind of just like memorizing stuff. We're going to put it all together in a minute, but the next thing before we get to that chart is what is called reference angle. So the reference angle is the angle between the x-axis and the terminal arm of the angle. So what the heck is the terminal arm? Well, that's the cut mark. So when we draw the angle, that's called the terminal arm that you're drawing. And I was saying it's like where you cut the Joe Louis. That's the terminal arm. So the reference angle, if I drew, let's say we draw the angle 3 pi over 4, where would that be? So how many pieces do I cut the pi into? 4. So here's my 4 pieces, and how many do I want? 3. So 1, 2, 3. This is called the terminal arm. And the reference angle is where? It's the angle between the x-axis, this is the x-axis, and the terminal arm. So there it is there, I just put a little theta. So what size is that piece of pi? 1/4. So the reference angle here is pi over 4. All right, let's draw one more. So find the reference angle for, let's do a negative 1, 'cause we've not done that yet. Negative 5 pi over 6. All right, so what does a negative do when it's a negative angle? Any ideas? You go backwards. So negative angle go so in the opposite direction. So from your start, you still start at your start line, but we go in the opposite direction. So negative angles go this way. So how many pieces is this pie cut into? 6. So 1, 2, 3, 4, 5. We only want 5, so we want to stop here. And this is the angle negative 5 pi over 6. Okay. What's the reference angle? So the reference angle is between that arm that we just drew. No. Yeah. So it's between that arm and the x-axis here, and it never has a sign. It's just always whatever the size of the piece is. So it's this angle. How big is this angle?
Pi over 6.
Right. So the reference angle here is pi over 6. It's one piece of the pie. Now, if the angle is reduced, like if that's a reduced fraction, it'll always just be whatever's on the bottom. If it's not reduced, it won't be. So, for example, if I said, say I said 10 pi over 4. That's not a reduced fraction. So when I draw it, the reference angle won't be pi over 4, because it's not reduced. You have to actually look at what it is, or reduce the fraction, then you'll know what the reference angle is. Yep.
You have if for say for that one, would it just keep going past 360 if you not go past 360?
Yeah, you can. So I'll show you one of those next. Okay, so 10 pi over 4, what would it be if we reduced it? 5 pi over 2. So those are equal. But if you didn't notice that you could reduce it and you went to draw it, then the reference angle won't be pi over 2. Okay. This one's a bit strange anyway. We're not really going to talk about reference angles when it's this. Where would this land? 5 pi over 2. So that's the pie cut in 2. So that's just these pieces, these big pieces. So 1, 2, 3, 4. Oh yeah, so this one does exactly what you're asking. We're only up to 4 one whole way around, but we want 5 pieces. So where do we go? Like Joe Louis can just keep piling up on top of each other. So you get to have one more. That would be 5. You see it? So we land right here. So the reference angle, either way, you look at it, is between that line and the x-axis, which both ways is the same. How big is the piece? So the reference angle here is pi over 2. Okay. But what we're going to talk about here is the actual terminal arm. Anyway, don't worry about that. So it lands on pi over 2, so that's what we're going to use, pi over 2. Okay. So 7 minutes left, so we're going to put this all together next class, but what we are going to do right now is this. So go back to your sheet, and do you see this table? You either need to memorize this table, and I would start now, like every day, so that you get, if there is a third of the test on Trig, final, you need to know this or you get 0. So either you need to memorize your unit circle or this table, like today. So that next class you actually could, if I said right at the start of class, write down your table, you could write it all down. Now how do you memorize things? Any ideas?
Before you go to bed.
Yeah, it could be. It actually could be any time, but what would you do before you went to bed, say, for instance? What do you do to memorize something? Yeah, no, yes. You didn't hear what he said, so it's not embarrassing him because no one even heard him. You both spoke at the same time. I usually can't filter that out, but I actually heard both. So, yes, you have to write it down. So what are you going to write down? You're going to recreate the table. There it is, blank. You're going to write this table. That's the first thing you have to do is know how to write the table to fill it in, and then you're going to fill it all in. And then you're going to have to look at it first to fill it in, and then you're going to look at it first to fill it in, then you're going to try it without looking. And then you're going to try it without looking again. And then you're going to sleep on it, which the sleep thing is good, because then in the morning when you wake up, have this in the, but it takes you 2 seconds. Try to fill in as much as you can after you slept. Then do the same thing. You need to do this like 8 times before you can memorize something to long-term memory, and you really need to know this.
Is that supposed to be 3 pi over 2 and
Oh,
4?
yeah, good. Let's fix that. Typo. That was a copy-paste error. Okay, so what I'm going to do before we go today is show you how I memorized it, okay? Yes?
Would that be something you'd give us when you go on the test?
Never.
Or would you just have to like make?
So what I would suggest you do is, because you practice so many times, you can recreate this table from nothing. And then what you would do on the final exam is get in there, and you're going to write everything on the back of the final exam that you have memorized. And then you don't need to stress about what you know and don't know, because you've written down the quadratic equation, you've written down this, you've written down anything else that you felt you needed to memorize, like how to find the vertex or something. You spend the first 15 minutes of the test without even looking at the test questions. All you do is write down everything you know. Then, when you're doing the test, you can flip back and say, oh yeah, that's right, rather than being worried about keeping all of that for 3 hours in your mind, okay? So just quickly, because it takes less than 3 minutes for me to do this, I'm going to show you how I have it memorized. And either you can jot down notes or go to the video and listen to me say it again when you try it. But this is what I do, okay? So I memorized this and I practiced it for days. Our teacher used to make us write it every morning when we got to class, first thing in math class, every day until you knew it. She would give you a blank one, but I'm not giving you anything. 0, 1, 0, 1, 0. How easy is that?
Yep.
And the opposite for code. Now, the second one in each of these rows is negative. 1, 2, that's negative. 1, 2, that's negative. All right, so I've got lots of it memorized already. Now, in here is a little harder, okay? So this is what I know. So, and you can do it however you want, but I'll just show you. So cos is C is my favorite letter because my name starts with C, and cookies and cake and calculus, all my favorite things. So C, and here's the fractions. You have to memorize what the 3 fractions are. Oh, these are the 3 fractions, okay? So, I mean, you have to memorize these 3 and then where they go. But this is how I start. Which one of the 3 do you like better?
First one.
Yeah, everyone has to say that, and if you don't, you're lying, because you for sure would like a half better. And I like C. And I know, I just remember that goes right here. Okay? So that's my starting point. So then, that's the 1/2. So the root 3 over 2 goes here, and sine is opposite. So I remember one of those, and then I can fill in the 4. That's how I do that. And what do you think about the other 2? They go here. They're the same. That's where sine and cos, their graphs like actually cross at some point, right? They look like a wave, and at some point they cross, and where they cross is right in the center. At pi over 4, right? That's the center of 90 degrees, and that's where they cross. Every time they'll cross over there. so those are equal. So that's how I do that, but what about tan? It's sine over cos, and here's the fraction, because I put sine on top. So this is 0 divided by 1. 1 divided by 0, you can't do it undefined. 0 divided by 1, 1 divided by 0, 0 divided by 1. What about this one in the middle? 1, because it's the same thing on top and bottom. You don't need to worry about it so much. And I already told you how to do these ones. Don't think too hard. What cancels? The 2, so what do we have on top? 1 over root 3. Root 3 over 1. And there, I've recreated it. So that's how I memorize it, so you can do it however you want. You have to remember what the 3 values are and at least give yourself a starting point to put them in. But I promise you, if you practice this a bunch of times, you'll make your life easier for the rest of time when you have to do math.